What happens when humanity's biggest dreams collide with the forces fighting back? Physics, politics, economics, geology, time itself. We're not talking about ordinary construction projects. We're talking about structures so massive they reshape continents. Machines so complex they push the boundaries of known science. Cities rising from empty desert, airports sinking into the ocean, tunnels buried beneath frozen seas, and a space station slowly cracking 400 kilometers above your head. Trillions of dollars, millions of lives displaced, decades of labor, and in some cases, no guarantee any of it will work. These are the megaprojects that define our era. But here's what most people never hear. Behind the stunning images and bold announcements, there are hidden engineering nightmares, financial black holes, say political battles that nearly killed entire projects before a single brick was laid, and ticking time bombs that engineers are quietly monitoring right now. What you're about to see goes far beyond the headlines. These are the real stories behind humanity's most audacious constructions, the victories, the failures, the risks no one wants to talk about. If you're fascinated by engineering on the edge of possibility, subscribe to Next Blueprint and hit like. Let's dive in. Kashagan Oil Field, Kazakhstan. Beneath the frozen waters of the northern Caspian Sea lies one of the largest oil discoveries of the 21st century. Over 30 billion barrels of proven reserves, enough black gold to reshape global energy markets for decades. But there's a reason Kashagan has earned a darker reputation in the engineering world. Some call it the most cursed oil field on Earth. The problems start with geography. For more than 5 months each year, the Caspian Sea freezes solid, temperatures plunge to minus 40 degrees, and the water here is shallow, less than 4 meters deep in some areas. Traditional offshore drilling platforms simply cannot operate. Engineers had to design something never attempted at this scale. Artificial islands, entire land masses constructed from rock and steel, rising from the seabed to serve as drilling and production bases. But geography was just the beginning. The reservoirs sit more than 4 kilometers underground. Pressures are extreme, and the oil comes mixed with hydrogen sulfide, one of the most toxic gases known to industry. A single uncontrolled leak wouldn't just be an environmental disaster. It could be fatal within seconds to anyone nearby. Equipment had to be fabricated from specialized corrosion-resistant alloys. Safety monitoring systems run constantly, watching for the smallest anomaly. Originally, Kashagan was supposed to come online in 2005. It didn't produce commercial oil until 2016, 11 years late. Multiple international contractors exited the project. Equipment failures forced costly redesigns. Pipelines cracked, budgets exploded. Total investment has exceeded $50 billion. Some estimates push it even higher. Kashagan now operates, feeding oil through pipelines to refineries and export terminals. But it remains one of the most expensive and most delayed energy projects in history. The oil exists. Getting it out without disaster is another story entirely. Kashagan fights ice and poison gas. But beneath the Baltic Sea, engineers face a different battle entirely. Fehmarnbelt Tunnel, Denmark to Germany. Right now, one of the most ambitious tunneling projects ever conceived is taking shape beneath the cold waters of the Baltic Sea. When complete, the Fehmarnbelt Tunnel will stretch 18 kilometers between Denmark and Germany. The longest immersed tunnel on the planet. A direct rail and highway link cutting travel times between Scandinavia and Central Europe by hours. But this project almost never happened. The original plans date back decades, yet construction didn't begin until 2021. What took so long? Politics, environmental protests, and a wall of opposition from Germany that nearly killed the entire vision. German ferry companies fought the tunnel for years. Environmentalists raised concerns about disrupting marine ecosystems. Lawsuits piled up, local governments pushed back. Denmark was ready to build. Germany kept saying no. The legal battles dragged on for so long that engineers had to repeatedly update designs just to keep pace with evolving safety standards. When approvals finally came, costs had ballooned. Initial estimates hovered around 7 billion euros. Current projections exceed 10 billion. And the engineering itself is staggering. The tunnel isn't being bored through rock like a traditional underground passage. Instead, 89 enormous concrete segments are being prefabricated on land, each one the size of a small building. These segments will be floated into position and sunk into a trench carved along the seabed, then connected one by one, in a chain stretching across the strait. The precision required is extraordinary. A few centimeters of misalignment could compromise the entire structure. And all of this is happening underwater, in unpredictable currents, against strict environmental regulations designed to protect the surrounding waters. If it succeeds, the Fehmarn Belt Tunnel will transform European transportation. If something goes wrong at this scale, the consequences could take decades to fix. A tunnel that took longer to approve than it will take to build. Political battles delayed this tunnel for decades. But the next project didn't wait for approval. It started sinking from day one. Kansai International Airport. Japan. In 1994, Japan unveiled one of the most audacious airports ever built, Kansai International. Constructed entirely on an artificial island in Osaka Bay, 5 kilometers offshore, covering more than 10 square kilometers of newly created land, a technological marvel designed to solve noise complaints by moving the entire airport away from populated areas. There was just one problem. It started sinking almost immediately. Engineers knew the seabed was soft, 60 meters of clay beneath the surface. They drove over 90,000 sand columns into the seafloor to stabilize the island. They calculated settlement rates, they built in tolerances, but the ground sank faster than predicted, much faster. In the years since opening, Kansai has dropped over 12 meters. That's not a typo. 12 meters, and it hasn't stopped. The airport now sits noticeably lower than its original elevation. Billions of yen have been spent on constant adjustments, jacks installed beneath buildings, columns extended, seawalls reinforced. The terminal itself, designed by legendary architect Renzo Piano, stretches 1.7 kilometers long, one of the longest airport buildings on Earth. Keeping it level is a relentless engineering operation. And then came the second island. When capacity demanded expansion, a new artificial island was constructed nearby for an additional runway. But this island is sinking even faster than the first. Engineers are now quietly debating long-term viability. Climate change is pushing sea levels higher. Typhoons are growing more intense. Osaka Bay is not getting calmer. Kansai remains operational. Millions of passengers pass through every year, but beneath their feet, a slow battle continues. Gravity versus engineering. One, the ocean versus human ambition. An airport that cannot stop sinking. Only endure. Japan fights sinking land. Meanwhile, scientists in France are trying to bottle the power of the sun itself. ITER fusion reactor. France. In the hills of southern France, 35 nations are constructing the most complex machine humanity has ever attempted. ITER. The International Thermonuclear Experimental Reactor. A device designed to recreate the energy process that powers the sun. Fusion. If it works, fusion could provide nearly unlimited clean energy. No carbon emissions, no long-lived radioactive waste. Fuel derived from seawater. A single gram of fusion fuel releasing energy equivalent to 8 tons of oil. That's the promise. The reality is more complicated. ITER was originally supposed to begin plasma experiments in 2016. The current target is now 2035. Nearly 2 decades of delays, and the budget has followed a similar trajectory. Initial estimates put the project around 5 billion euros. Current costs exceed 25 billion. Some analysts believe the final figure could climb even higher. The engineering challenges are unlike anything attempted before. At the heart of ITER sits a tokamak, a donut-shaped chamber where hydrogen isotopes are heated to 150 million degrees Celsius. That's 10 times hotter than the core of the sun. At these temperatures, matter becomes plasma. To contain it, engineers rely on superconducting magnets generating fields powerful enough to suspend the plasma in midair. Any contact with the chamber walls would instantly cool the reaction and damage the equipment. Building these magnets requires precision manufacturing at tolerances measured in fractions of a millimeter. Components are fabricated across multiple countries and shipped to France for assembly. Coordinating this international supply chain adds layers of complexity. A delay in South Korea affects construction in Europe. A design revision in Japan ripples through the entire project. And here's the uncomfortable truth critics often raise. Even if ITER succeeds, it's only an experiment, a proof of concept. Commercial fusion power plants are still decades away. Some skeptics argue that by the time fusion becomes viable, solar and battery technology will have already solved the energy problem. Others believe fusion research is essential, regardless of timeline. The debate continues. The promise of unlimited energy. Forever 20 years away. Fusion promises to solve energy forever. But one country decided not to wait. They moved an ocean instead. China's south to north water diversion. Northern China has a problem. Hundreds of millions of people, massive industrial cities, sprawling agricultural regions, and not nearly enough water. The north holds only 20% of China's fresh water, but it contains nearly half the population. The solution? Move the water. The south to north water diversion is the largest water transfer project in human history. 3 routes: eastern, central, western. When fully complete, the system will be capable of moving over 44 billion cubic meters of water annually, an almost incomprehensible volume. The central route alone stretches over 1,400 kilometers. Starting from the Danjiangkou Reservoir in Hubei Province, running northward through tunnels, aqueducts, and canals, crossing beneath the Yellow River through a massive inverted siphon buried 70 meters underground, terminating in Beijing and Tianjin. And here's what makes the central route remarkable. It operates entirely by gravity. No pumps, just meticulously calculated gradients. Engineers designed the system so water flows downhill the entire way. Tolerances measured in centimeters over distances spanning hundreds of kilometers. But the project has a darker side. Over 350,000 people were relocated to make way for expanded reservoirs and canal routes. Entire villages disappeared. Communities that had existed for generations were dissolved overnight. Compensation programs faced criticism for inadequacy. Some relocated families struggled to rebuild their lives in unfamiliar regions. Environmental costs are also becoming visible. Rivers feeding the system now carry less water to their original destinations. Ecosystems downstream are showing stress. Some scientists argue the project merely shifts the water crisis rather than solving it. Northern cities grow dependent on southern water while southern regions face their own emerging shortages. And the western route? Still unbuilt. Technically and politically complex, requiring tunnels through mountainous terrain near Tibet. Facing opposition from downstream nations concerned about reduced flows into their territories. Total investment has exceeded $70 billion. The project works. Beijing now receives over 70% of its water from this system. But critics warn that long-term sustainability remains uncertain. A project so large it reshapes geography. But at what hidden cost? If you're learning something new, hit like and let us know in the comments. Do you think these mega projects are worth the risk? China moved water across a continent. Libya pulled it from somewhere far more dangerous, beneath the oldest desert on Earth. Libya's great man-made river, the Sahara, the world's largest hot desert, thousands of kilometers of rock and sand. And beneath it, one of the most audacious engineering systems ever constructed. Hidden from view, buried underground, a network of pipelines stretching over 4,000 kilometers, delivering 6.5 million cubic meters of fresh water every single day. The Great Man-Made River, Libya's lifeline. This isn't a river in any traditional sense. It's a vast plumbing system, over 1,300 wells, some drilled more than 300 meters deep, tapping into ancient aquifers buried beneath the desert. Water that fell as rain thousands of years ago when the Sahara was green, now pumped to the surface and piped to coastal cities. The scale is staggering. Pipes 4 meters in diameter, each segment weighing 80 tons, prefabricated in factories and laid in trenches up to 7 meters deep. Pumping stations, reservoirs, control towers, a hidden infrastructure web supplying over 70% of Libya's population. But there's a problem no engineering can fix. This water is ancient, fossil water. It accumulated over millennia when the climate was different, and it's not coming back. These aquifers have no significant recharge. Every liter pumped to the surface is a liter that will never be replaced. Estimates suggest the system could run dry within 50 to 100 years, perhaps sooner if extraction rates increase. And then came the war. Libya's civil conflict devastated the country's infrastructure. Pumping stations were damaged, pipelines breached, maintenance crews couldn't access critical facilities. Sections of the network fell into disrepair. The system still operates, but vulnerabilities have multiplied. Funding for repairs remains uncertain. Skilled technicians have left the country. Libya built a miracle beneath the desert, but it's drinking water that will never come back. Libya races against time underground. But one tower in Saudi Arabia has been frozen in place for years, halfway to the sky. Jeddah Tower, Saudi Arabia. Since 2008, the world's tallest building has been the Burj Khalifa, 828 meters of steel and glass rising above Dubai, a symbol of ambition, a statement of possibility, and a challenge. Saudi Arabia decided to answer that challenge, not by matching the Burj, by exceeding it, dramatically. Jeddah Tower was designed to break 1 kilometer, 1,000 meters, the first building in human history to reach that threshold. a structure so tall it would redefine what cities could become. Construction began in 2013. Foundation work completed. Structural columns rising. Progress photographs circulating worldwide. And then, in 2018, everything stopped. Cranes went silent. Workers left the site. The tower froze in place, roughly 1/3 complete. And it has remained that way for years. What happened? Reports point to multiple factors, but legal disputes involving the primary contractor, the arrest of prominent Saudi businessmen during an anti-corruption campaign, funding uncertainty tied to broader economic shifts. The project's parent company faced turbulence that rippled through to the construction site. But beyond the financial and legal drama, engineers have quietly raised technical concerns. Building at this height pushes structural engineering into uncharted territory. Wind forces at 1 kilometer don't scale linearly. They intensify in ways that require extraordinary solutions. The tower's design includes a tapered form intended to reduce wind load, a concrete core surrounded by a steel framework. But some experts question whether the original calculations account for every variable at this unprecedented scale. Elevator logistics present another puzzle. When moving people efficiently through a structure this tall requires innovation beyond current systems. Sky lobbies, transfer floors, high-speed pressurized cabins. The Burj Khalifa already pushes existing technology to its limits. Jeddah Tower would need to leap beyond. Will it ever be finished? Saudi officials insist the project remains active. Occasional updates suggest preparations for resuming work. But years of silence have fueled skepticism. The race to 1 kilometer remains frozen, halfway to the sky, waiting for something to change. One tower frozen in the desert, another megastructure holds back an entire river, and geologists have started warning about earthquakes. China's Three Gorges Dam numbers first, 2,400 meters long, 185 meters high, maximum reservoir capacity of 39.3 billion cubic meters, more than 27 million cubic meters of concrete, an installed power capacity of 22.5 gigawatts, 32 turbine generators producing over 100 billion kilowatt hours annually. The Three Gorges Dam is the largest hydroelectric complex on Earth, a monument to engineering ambition, a system designed not just for power, but for flood control, navigation, and water management across one of China's most vital river basins. But monuments cast shadows. Before the dam was built, geologists warned that filling a reservoir this massive could trigger seismic activity. The sheer weight of water pressing down on underlying rock, the lubrication of fault lines by water infiltration. It's a phenomenon called reservoir-induced seismicity. And after the reservoir began filling, earthquake frequency in the region increased. Most tremors were small. But in 2008, a devastating earthquake struck Sichuan province. Over 87,000 people killed or missing. While the epicenter was outside the immediate reservoir zone, some scientists have suggested a possible connection. Others dispute the link. The debate remains unresolved. What's undeniable is that seismic monitoring around Three Gorges has intensified. Then there's the human toll. Over 1.3 million people were relocated to make way for the reservoir. Entire cities submerged, communities erased, ancestral lands flooded. The resettlement program remains one of the largest forced migrations in modern history. Many displaced families received compensation, but reports of inadequate support and difficult transitions persist. Environmental consequences continue unfolding. Silt that once flowed downstream now accumulates behind the dam. On the long term, this buildup could reduce reservoir capacity and affect downstream ecosystems. Endangered species like the Yangtze River dolphin and Chinese sturgeon have seen habitats disrupted. Some populations may never recover. And in 2020, record flooding tested the dam's limits like never before. Water levels rose to critical thresholds. Spillways operated at maximum capacity. Official statements assured the public the dam performed as designed. But satellite imagery and leaked internal discussions suggested the stress was more severe than publicly acknowledged. The world's largest dam. But some engineers quietly ask, what happens if it fails? This is exactly the kind of story most people never hear. If you want more deep dives like this, subscribe to Next Blueprint. Three Gorges holds nature at bay. But Saudi Arabia isn't holding anything back. They're building an entire civilization from nothing. Saudi Arabia's NEOM and the Line. In the empty northwest corner of Saudi Arabia, where desert meets the Red Sea, something unprecedented is taking shape. NEOM. a planned mega-region covering 26,500 square kilometers, roughly the size of Albania, designed from scratch, no legacy infrastructure, no existing city to retrofit, just empty sand and an audacious vision. And at the heart of NEOM sits the line, 170 kilometers long, 200 meters wide, 500 meters tall, a continuous mirrored structure stretching across desert and mountain, housing up to 9 million people, no cars, no roads, no carbon emissions, high-speed rail running end to end, designed so residents can traverse the entire city in 20 minutes. Nothing like this has ever been attempted, not even close. The concept challenges fundamental assumptions about urban design. Traditional cities sprawl outward. The line compresses everything into a single linear form. Residences, offices, schools, parks, medical facilities, all stacked vertically and arranged along a single axis. But independent engineers have raised serious questions. How do you cool a glass-walled city in temperatures exceeding 50 degrees Celsius? The energy demands for climate control alone could be astronomical. Where does the water come from in one of the driest regions on Earth? Desalination at this scale requires immense power. How do you manage emergency evacuations in a structure this dense and elongated? What happens when 9 million people need to move simultaneously? Reports have also surfaced alleging troubling aspects of the project's execution. Tribal communities displaced from ancestral lands, allegations of inadequate compensation, concerns about worker conditions at construction sites. Saudi officials deny wrongdoing, but international observers continue raising questions. Timeline and budget pressures mount. Original completion targets have slipped. Costs have ballooned beyond the initial $500 billion estimates. Some sections are under construction, others remain conceptual. The gap between announcement and reality grows wider each year. NEOM represents either the future of urban living or the most expensive experiment in architectural hubris ever attempted, possibly both. The most ambitious city ever announced and the most questioned. NEOM is building the future on sand. But humanity's greatest engineering feat isn't on Earth at all. It's floating 400 kilometers above us. The International Space Station, 400 kilometers above Earth's surface, traveling at 28,000 kilometers per hour, completing one orbit every 90 minutes, 16 sunrises and 16 sunsets every single day. The International Space Station, humanity's greatest collaborative engineering achievement. Built by 16 nations over 15 years. Assembled piece by piece through dozens of launches, dockings, and spacewalks. Total cost exceeding $100 billion. The most expensive single object ever constructed, weighing over 420 tons. Solar arrays spanning the length of a football field. Living quarters for 6 astronauts. Now, laboratories conducting experiments impossible to perform under the influence of gravity. Life support systems recycling water, generating oxygen, removing carbon dioxide, a closed-loop ecosystem hurtling through the void. Since November 2000, the station has never been unoccupied. Over 280 astronauts and cosmonauts from more than 20 countries have lived and worked aboard. More than 3,000 scientific experiments completed. Discoveries in medicine, materials science, biology, physics. But the ISS is aging. Some modules have been in continuous operation for over 25 years, far beyond their original design life. Systems that were cutting edge in the 1990s now require constant maintenance. Replacement parts are increasingly difficult to source. And then there are the cracks. In recent years, Honda engineers have detected fractures in the Russian Zarya module, small enough for now, monitored closely, but concerning. The causes remain under investigation: stress from thermal cycling, metal fatigue from decades of vibration, or something else. Geopolitical tensions add another layer of uncertainty. The partnership between NASA and Roscosmos, once a symbol of post-Cold War cooperation, has frayed. Disagreements over funding, disputes over responsibilities, the war in Ukraine casting a shadow over every joint decision. Russia has periodically threatened to withdraw from the partnership. Whether those threats are serious or negotiating tactics remains unclear. The ISS is scheduled for decommissioning around 2030. The plan involves a controlled deorbit, a fiery descent into the Pacific Ocean, and targeting a remote area known as the spacecraft cemetery. Other retired stations and satellites rest there on the ocean floor. But here's the problem. No fully operational replacement exists yet. NASA is working with commercial partners to develop successor stations. Axiom Space and others are building modules. But these projects are still in progress. A gap looms, a period where humanity might have no permanent presence in low Earth orbit for the first time in decades. Humanity's greatest collaboration, entering its final chapter. 10 megaprojects, trillions of dollars, decades of labor, and not a single guarantee. Look closely at these stories and a pattern emerges. Ambition always meets limits. Physics pushes back. Politics intervenes. Budgets collapse. Timelines stretch. And yet, humanity keeps building. Some of these projects will succeed beyond expectations. Others may become cautionary tales. A few might be remembered as visionary, others as reckless. The line between genius and hubris often only becomes clear in hindsight. And here's the question no one can answer yet. Will the next generation complete what this one started, or inherit its failures? The Three Gorges Dam might stand for centuries, or face challenges we can't yet predict. NEOM might redefine cities, or become history's most expensive ghost town. The ISS will fall. What rises in its place depends on decisions being made right now. These megaprojects are never truly finished. They evolve, they adapt, they face crises, they demand more resources, more innovation, more sacrifice, and sometimes they collapse. Somewhere right now. Another impossible blueprint is being drawn. Another engineer is arguing with a politician. Another investor is calculating risk. Another community is being told their land is needed for something greater. The next mega project is already taking shape. You just haven't heard about it yet. If you want to keep exploring the engineering, technology, and mega projects shaping our future, subscribe to Next Blueprint, hit like, and tell us in the comments. Which project do you think will succeed, and which is destined to fail?